Hey everyone, welcome back, and today let's solve Leetcode problem 951 titled Flip Equivalent Binary Trees. So for a binary tree T, we can define a flip operation as follows. Choose any node and swap the left and right child subtrees. So a binary tree X is flip equivalent to a binary tree Y if and only if we can make X equal to Y after some number of flip operations. We're given the roots of two binary trees, root 1 and root 2, and we need to return true if the two trees are flip equivalent or false otherwise. So pretty straightforward problem statement here, and let's go ahead and better visualize this in the examples to see how it really works. So in example 1, we have the input root 1 and root 2 to be as follows, and they actually give us an image for example 1 to help us better visualize and depict how this actually works, but we return true because we simply flip at nodes with values 1, 3, and 5. So at 1 we flip its subtrees, which is going to be 2 and 3, and for 3 we're going to flip its subtrees, which is going to be 6, and for 5 we're going to flip its child trees, which are going to be 8 and 7, and so from root 1 we can go to root 2, and so this would actually be a flip equivalent input. And in example 2, we have both roots to be simply empty, and obviously we don't need to do anything, they're already flip equivalent, and they would hence be flip equivalent, and so we'd output true. However, for example 3, we have one node to be a empty or null root and the other to have a root of 1. And since these values of the different roots are different because one is null and the other actually does have a value of 1, we'd output false because they are not flip equivalent. So we're given that the number of nodes in each tree is going to be in the range of 0 to 100 inclusive, and each tree is going to have unique node values in the range of 0 to 99 inclusive. So with that out of the way, I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution, and then I'll show you guys how I would optimally solve this problem in a few seconds. Okay, so to solve this problem efficiently, we're going to use recursion to effectively explore two trees simultaneously and basically check if they're either identical as is or if they become identical after flipping their subtrees. Okay, so with that out of the way, let's just go ahead and dive straight into the code here. So I understand that a lot of you guys probably don't really understand what lines 1 through 6 really do, as they are also commented out. But just to give you guys a gist of how this really works, on line 2, we simply basically define our tree node class, and that's going to represent each node of our binary tree for every input, or I guess test case, if you will, right? And on line 3, inside the class, we have an init constructor method. In Python, it's init to really have your constructor method, and this function basically initializes the node's values and its left and right children. Okay, and on line 4, we have the val or value parameter to actually hold the value of the node. And if no value is passed, as you can see here, we have a default or a value to be defaulted to 0, right? And on lines 5 and 6, we have the left parameter to represent the left child of the node and the right to represent the right child of the node. And these also default both to none if we don't actually have any values specified in any input binary trees. Right, and essentially this tree node class will help us construct our binary trees and easily access their children nodes, right? So with that out of the way, let's just go ahead and dive straight into the code here, right? So first I'm just going to have a quick base case here. So if not root 1 and, oops, there should not be a space, I don't know why I put a space there. If not root 1 and not root 2, we know we can immediately return true. But why can't we immediately return true? That's because both of these nodes are null, right? And to better explain that, we've reached the end of both trees, and so they're going to be equivalent. And so in that case, we can return true, because again, both of these nodes are none, right? So after that, we also have to check a case where they're actually not equivalent. So if not root 1, like we talked about before in the example, so if not root 1 and root 2, that's effectively saying that one of the roots or trees is null and the other node is going to be non-null. So if not root or, in fact, I'm going to format this a little bit better. So if not root or not root 2. That makes a little bit more sense. Or the value at root 1, so root 1.val, if it doesn't match the value at root 2, so root 2.val, we know that these are not flip equivalent, and we can immediately return false. Oops, I don't know what I did there. Sorry about that. We can return false. Right, and again, effectively, we have to check these three conditions. If only one of the nodes is none, or if the values of these corresponding nodes are different, then we have to return false. Also, if any of these conditions are true, then the trees are not equivalent. They're not flip equivalent, and we have to return false. In this case, if we actually encounter this case for any node as we recursively traverse through all the different nodes in our binary trees, or our both binary trees. So again, if not root 1, or not root 2, or the values at these two nodes in root 1 and root 2 don't match, we have to return false immediately at that iteration. Right, and effectively we can simply apply our recursion formula now, so we have to simply return. Now it's going to be pretty lengthy, but it will make sense as you can see it. You should guess. Okay, we have to return self.flipEquiv, because that's what the function is called right here on line 8, as we recursively call it. So again, I'm going to call it self.flipEquiv. In fact, I'm actually going to just copy this, so it's a little bit easier to actually access it. Self.flipEquiv. Make that a little bit better. So we'll pass in the first two parameters as our first recursive call, root 1 dot left and root 2 dot left, and we'll also pass in self dot copy that. For our next parameter, we're going to pass in root 1 dot right and root 2 dot right. And I'm going to just quickly slash here to move on to the next line. Or, oops, I forgot my or. Or, I'm going to return, okay, this should be, okay, you know what, never mind. Or, we have to again say if self.flipEquiv. In this case, our parameters now are going to be root 1 dot left and root 2 dot right. I'm trying to type this pretty slow so I actually have my syntax formatted correctly. And finally, self.equip, or whatever it's called. In this case, I'm going to pass in root 1 dot right, oops, and root 2 or 2 dot left. So this is a pretty lengthy and ugly looking recursive call on all these different left and right nodes for our current node in root 1 and root 2. But it's pretty straightforward. We simply have to recursively check there's two different scenarios, right? So first is we have to check the no flip scenario, where we compare the left child of root 1 with the corresponding left child of root 2, and the right child of root 1 with the corresponding right child of root 2. And for our second case, in the or conditional, we have to have our flip scenario. So that's going to be as we compare the left child of root 1 with the right child of root 2, and the right child of root 1 with the left child of root 2. And so if either of these scenarios do return true, it means that the trees are equivalent, either with or without flip. And so we can immediately return true. And otherwise, for any of these nodes, as we recursively traverse through all the different left and right nodes for each node in our both binary tree inputs, we have to return false. So basically, to better overall what this overall explain what this code does, simply this function flipEquiv is going to be recursive, right? And we use that, and we see that with the self keyword as we recursively call it in this return method, right? And it basically compares corresponding nodes of two binary trees. In this case, that's going to be root 1 and root 2. And for each node, our function is going to check first if both nodes are none. It can return true because both of them are null. They obviously are flip equivalent because they have the same no value. Also, if the trees are equivalent after flipping the children of the nodes, or they're equivalent just directly as is without any flips, then we have to return true. But we have a condition when they're false. If one node is none and the other is not null, or if their values itself at that node aren't equal, we can return false immediately. Okay, and this recursion effectively continues until it actually either finds a mismatch or it eventually reaches the leaves of both of the trees, basically the ending of both of the trees. And in that case, that means they are flip equivalent if both of our nodes are non-null, and we can return true once we're done traversing through the entire or both of the input binary search trees recursively and checking for any mismatches. If we don't find any mismatches and return false like that, we can return true after we actually hit the end of both nodes, indicating that they are indeed flip equivalent. So if I were to submit this right now, unless I made any dumb syntax errors here on line 13 through 15, yeah, that's probably what I did wrong. Okay, yeah, okay, this should be not equal to. I forgot an exclamation mark here. I probably spelled something wrong again as well, but as you can see, this is just about as efficient as you can get. So for the time complexity of this solution, this is going to be big O of the minimum of n1 and n2, right? Where n1 and n2 are going to be the number of nodes in the two trees. And that's basically because we need to visit every single node in both the trees to ensure that they are actually equivalent. And the space complexity is going to be big O of, again, also minimum of h1 and h2, where again, h1 and h2 are the heights of the two trees. And that's because this space rather, is going to be used by the recursive call stack using or during this traversal, right? So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.